Hello and welcome back. I'm Matthew Lay, and today we're going to study series circuits. So let's get started. We have some objectives. First, we want to define a series circuit. Next, we want to list the characteristics of a series circuit. Then we want to calculate total resistance, current, and power for a series circuit, and we want to calculate the voltage level drops and power dissipated by the series circuit. Also, we want to redefine, because we've spoken about this before, an open circuit, especially as it pertains to a series circuit, and a shorted circuit or a shorted series circuit. When we look at how two components can be connected together electrically, we can view these two varying ways of riding a motorcycle. And the one here to the left is we have two individuals, one a dog and one a human, that are both wanting to ride on one motorcycle, and they use a sidecar and they ride side by side. That's one way to ride a motorcycle. And then we have here two individuals that are riding on the same seat, one in front of the other. And so there are two different ways for two components or two individuals to get that done, riding a motorcycle. And there are two different ways that we can actually connect components electrically. And we're going to study both those types of circuits. So we know that this is our symbol for a power source, a battery, and these are our symbols for resistors. I want you to pause the video here and take a moment and see how many different configurations you can come up with of connecting these resistors to this battery. Okay, and you should be able to only come up with two distinctly different circuits. But go ahead and pause the video and then come back and we'll look at this. Okay, so if given the source and the two resistors, how many different configurations can be made? This first source here is called a series circuit. And what a series circuit is, when you take one component and you take the ending of one component and connect it to the beginning of the next component. The head of the first component is connected to the positive of your power source, and the end of the second component is connected to the negative. That makes those two components configured in series, is how we say that. The other way that we could do that is we could take the beginning of both of our components, in this case resistors, and connect them to the positive of our power supply. And then on the other end, both of the opposite ends of those components would be connected to the negative of our power supply, and we call this a parallel circuit. So this is the circuit that we are going to be speaking of today, and in a future lesson we'll talk about a parallel circuit. So series circuits have many characteristics, and this is the first characteristic, and it's how resistance is expressed in a series circuit. The series circuit resistance is additive. Okay, so to attain the total resistance in the series circuit, all you have to do is add those individual resistors. Now remember, R is our letter that represents resistance in math formulas. This subscript T means total, and the subscript 1 and 2 just means the first resistor and the second resistor. So you can see them here, R1 and R2. And if we add those two together, it would be the same as connecting them in series and then connecting our ohm meter across those resistors, and we would measure the total resistance with our ohm meter. So if R1 is 220 ohms and R2 is 330 ohms, we would add those together, and our total resistance should be 550 ohms. Okay, let's look at current in a series circuit. So in a series circuit, current is common among all components. So in other words, the same current that goes through R1 is going to go through R2. So the total current can be calculated by dividing the resistance, the total resistance, into the source voltage, which is our total voltage. Okay. So our I, remember I is the letter that we use to represent current in our math formulas. E is the letter that we use to represent voltage in our math formulas. And R is the letter that we use to represent resistance in our math formulas. And the subscript of T means total. So if you notice, this formula uses total for all of them. So if you want to get the total current, you have to use the total voltage and the total resistance. And we can use that total resistance from the previous page and calculate what our total current is. Okay, so the total current is going to flow through every circuit every component in a series circuit. So the current that flows out of this power supply will flow through this meter. It will flow through that resistor, but that same current would flow through this meter, so those two meters would not read anything different from one another. And then it's going to flow through this resistor, and then the same current will flow through here. So all three of these meters should read the exact same current because the current is common in a series circuit. Okay. Each ammeter in this graphic will read the same current. Okay. Let's look at voltage. Voltage is going to be different. Okay. In fact, a series circuit could be considered a voltage divider. It's going to take the voltage that we're putting into this circuit and it's going to divide it up amongst these resistors here. Okay, each component's voltage drop can be calculated by using our Ohm's law triangle, and that is using our current and our resistance in the case of voltage. So E equals I times R. And so the voltage drop across E1 will technically be I1 times R1. Well, I1 and T1 are the same, so I'm just stating here that the total current, which is the same current through every component in this circuit, can be used, times the resistance value of R1 to get the voltage drop from R1. Okay, and then the same can be said for R2. Again, total current is going to go through R2, same current that went through R1. But if we have a different resistance value, then we use that value times that current, and we should get our voltage drop across R2. So how do these voltage drops add up? Well, the sum of the voltage drops in this series loop, sometimes we call a series circuit a loop, is equal to the sum of all of the voltage sources. In this case, I only have one voltage source. So if I have E sub t here, that voltage rise, or that voltage that I'm putting into this circuit, is going to equal the voltage drop there plus the voltage drop there plus the voltage drop there. There's no other place for voltage to be lost, so it's going to be dissipated across those three resistors. Okay, so there's my three voltage drops, and that should equal that voltage rise there. Okay. So, and Kirchhoff came up with this law, and he just said the sum of the voltage rises have to equal the sum of the voltage drops. So here I have actually two power sources. One, ET1 and ET2 is the second power source, and those add up as well. So the sum of the voltage rises, E sub T1 and E sub T2, is going to equal the sum of all my voltage drops in this particular case. So this might be, you could think of this as maybe your television remote. You have to put two AA's or AAA's in your television remote, and typically they go in series. Each one of those is 1.5 volts. You put them in series, that would add up. So your remote is going to operate off of 3 volts, and then you have a series of voltage drops in there for the particular circuitry that you have in your remote. So those voltage drops have to equal those two voltage rises. Okay, so to take a measurement, the total voltage provided with the circuit across each component within the circuit, therefore the sum of the voltages across each component will equal our total voltage. So I can measure, if we're doing a lab, I can measure my voltage drop here, and I can measure my voltage drop here with a meter. Remember, voltage measurements are taken in live circuits across a component. Current measurements are taken through a circuit in a live circuit, and then resistance measurements are taken in a dead circuit across the component. Okay, so those are our three different types of measurements we can do with our multimeter. Series circuit power. The power dissipated from each component can be calculated squaring the current, because the current is common in a series circuit, multiplying times each component resistance. So the power dissipated in resistor 1 is that I total squared times R. And this is just from our Ohm's wheel. And for the power dissipated across R2, again, it's that total current squared times R2. The power, the total power that's put out by this power supply is just going to be the sum of those power draws from each one of those resistors. So the total power is just going to be power 1 plus power 2. Okay, so the total power could be calculated by also dividing the source voltage squared by the total resistance. So our voltage squared, E sub T squared, divided by our total resistance, which is the sum of the two resistors, will also get us total power. And if we calculate it in these two ways, we can do a checksum on these at the end. So you can compare these two together and see if the sum of all the ones that you used current and resistance equal the sum of the total that you used with voltage and resistance. Okay, series circuits characteristics. The total resistance is the sum of the resistors. Okay, so we just add up R1 and R2 and we're going to get our total resistance. Okay, the total current is equal to our source voltage divided by that total resistance. Okay, so the total voltage we're putting into it and the total resistance we have across it's going to give us our total current. And our total current is current that flows through each component in the circuit, so there really is no formula for that. They're all equal to each other. So the current through 1, current through 2, and the total current are all equal to one another. Okay, and I'm using this to show conventional current flow going from the positive of the battery to the negative of the battery. So let's actually plug some numbers in a problem here. So you're going to get a lot of problems like this where you have a generic display or graphic and then the givens will be written down at the bottom. And we want to solve this circuit using this given data here. So I have a total voltage of 10 volts, a total resistance of 380 ohms plus my 560 ohms. And so first thing we want to do is find our total current. So we want to find that total resistance by adding the 380 and the 560, and that gives us 940 ohms. Okay, so now we can find total current. We can use our total voltage and divide that by our total resistance, and we will get our total current value. Okay, so our total current value will be that 10 volts divided by the 940 ohms, and that gets us rounded 10.638 milliamps. Okay. So now we want to find our individual voltage drops because we know that we have 10.638 milliamps going through each one of those components. So we can use that current, 10.638 milliamps times the 380 ohms, and that's going to equal 4.043 volts. And that's going to be my voltage drop across this resistor. And same formula, just have to substitute R1 for R2 to get the E2. And so I'm going to, again, take the same, remember the current's common in a series circuit, so the 10.638 milliamps times my 560 ohms, and that's going to give me 5.957 volts. And we're going to check our answers by adding those two together, and it should equal 10 volts. So we add those two together, and it does equal 10 volts. So that's very good. That means that we calculated those appropriately. Okay, so now let's figure out our power drops. Okay, so find power dissipated by each one of these components. A resistor only has one way to dissipate power, and that's heat. It doesn't give off light, doesn't give off sound, doesn't move anything. So that's why I say dissipated. Most people associate dissipation with heat rising. P1 equals I sub T or the total current squared times my R1. So the 10.638 milliamps squared times my 380 gives us 43.006 milliwatts of power dissipated in R1. And in the power across R2, all we have to do is use R2 in the same formula. The 10.638 milliamps squared times my 560 ohms is going to be 63.377 milliwatts. And we can check our answers. So we know that the total power is going to be the sum of those two, but we know we can also calculate it. And this is kind of a safe check here because this was given, and hopefully we can do the math appropriately to add the two resistors that we have here. So these are our givens that we're going to compare against something. We actually calculated this current, and if we calculated the current wrong, we would have wound up with wrong power dissipation. So if I take and add those together, I get 106.383. And then if I use this formula where I square 10 volts, which is my source voltage, and divide it by my total resistance of 940 ohms, I get the exact same answer, and that checks out. So that means our current calculation and our total resistance calculations were all appropriate. Okay, this is a way of denoting it on your paper as you go along. I used to do this when I was a student. I actually even used different colored pens. So I would write voltage in one color. You see here I have my source voltage, and then I have my voltage drops in red. I wrote down the ohm values in black, and then some other color, doesn't necessarily have to be purple. I would write the wattage value there, and then I would even draw a circle that the same current is going through all of those components, and I would show a conventional current flow by showing that the arrow was going from the positive to the negative there. That may help a student visualize the circuit and what's going on in the circuit and where those numbers relate to on it graphically. Okay, let's look again at an open circuit. So this is a little symbol for a fuse. It's actually kind of missing a little semicircle there. And so this is a fuse protected circuit that has a blown fuse. And since that fuse is blown, that means that it is open. You can see there's an air gap there, so it's open. In an open circuit, the definition is a circuit that has no path for current to flow. Okay, so in this case, once that fuse is blown, the power supply will no longer be serving current to the resistors, and there will be no path for current flow, and so therefore we won't have any voltage drop across our resistors or any power dissipated across those. Okay, a shorted circuit, conversely, we replace the fuse. We've got a good fuse here, but this red line is to depict that a wire is routing around or shorting resistor 1. And resistor 1 is now effectively taken out of the circuit because all the current is going to want to go down this wire instead of through this resistor. The current is much like us driving in traffic. If we see a traffic jam and we see an exit that we can get off and drive on an outer road which has no traffic, we're going to choose that path of least resistance. Well, electric current does the same thing. If there's very little resistance in one path and a significant amount of resistance in the other, it's going to choose the path of least resistance. And so that is shorting out R1. And a short is a circuit that has very low resistance causing very high current flow. Now in this case, we have another resistor here. And if this power source with that total resistance now, because this has been effectively removed, can still handle the output, we won't blow the fuse. But if we shorted this resistor and the power supply can't handle the current of just that resistor, we would blow that fuse and we would go from a shorted circuit to an open circuit. And that happens quite a bit. When we pop a circuit breaker at home, that means that we have shorted something, or at least drawn too much current out of one circuit, more than the wires can handle. And the circuit breaker opens up the circuit. So that's why we talk about an open circuit and a shorted circuit kind of in the hand in hand, because they do go together. Okay. So again, the definition for a short circuit is a circuit that has very low resistance causing very high current flow. And quite often that current flow either causes a popped fuse or an opened circuit breaker. Okay, so let's review. First, let's define a series circuit. Go ahead and pause the video, and we'll come back and in just a moment to get the answer. A series circuit is a circuit that has only one path for current to flow. Okay, so we're going to find that a parallel circuit is going to be different from that, so that distinguishes series circuit from a parallel circuit. List the characteristics of a series circuit. Okay, again, pause the video and then come back. In a series circuit, current is common, voltage is divided, and resistance and power are additive. That's saying it pretty succinctly. Current is common because we only have one current going through the circuit. Voltage is divided because across those resistors, the current causes a voltage drop, and the resistance and the power, we can just add those up. Okay? Define an open in a series circuit. Okay, again, pause the video and we'll come back. An open circuit is a circuit that has no path for current to flow. Okay, think of that blown fuse. Once we blow the fuse in a series circuit, there's no path for current. Okay, define a short, and this would be a short in a series circuit. A short has very low resistance causing very high current flow. And if the remaining resistance in that series circuit is too low for our power supply to supply that much current, we are going to have some sort of overcurrent protection taking over in that case. So this concludes part 1 of our series circuit series. We're going to have a second part where we're going to go more in depth into series circuits. But hope this was helpful, and we'll see you in the next video.